Hey everyone, welcome back to my YouTube channel. In our previous video, we discussed the fundamentals of numerical calculations, where we learned the proper engineering procedures, the importance of dimensional homogeneity, significant figures, and the correct use of SI units and prefixes. Now that we understand the basic principles, it's time to put them into practice. For today's video, we'll apply those concepts by solving several engineering examples involving unit conversions, density conversions, and calculations with SI prefixes. As we work through each problem, I'll also share important engineering rules and common mistakes that you should avoid. So, without further ado, let's begin with our first example. Convert 100 kilometers per hour to meters per second. Before we start solving, remember our first rule. Arrange the conversion factors so that the unwanted units cancel out. Never memorize conversion formulas. Instead, let the units guide your solution. We are given 100 kilometers per hour. Since we want the answer in meters per second, we need two conversion factors. We know that 1 kilometer equals 1,000 meters, 1 hour equals 3,600 seconds. Notice how we arrange the conversion factors. Kilometers cancel with kilometers. Hours cancel with hours. The only remaining unit is meters per second. This process is called dimensional analysis, and it is one of the most important techniques in engineering calculations. After simplifying, the final answer is 27.8 meters per second. Remember to keep several decimal places during your calculations, and round only your final answer to 3 significant figures. Now, let's convert 24 meters per second into kilometers per hour. Again, arrange the conversion factors carefully. We know that 1 kilometer equals 1,000 meters. 1 hour equals 3,600 seconds. Meters cancel, seconds cancel. The remaining unit becomes kilometers per hour. The final answer is 86.4 kilometers per hour. Whenever you solve unit conversion problems, always ask yourself, did all the unwanted units cancel? If the answer is yes, then you have most likely arranged your conversion factors correctly. Our next example is to convert the density of steel from 7.85 grams per cubic centimeter to kilograms per cubic meter. At first glance, this may seem like an ordinary unit conversion. However, this example highlights one of the most common mistakes made by engineering students. Before solving, remember this important rule. If the unit is squared or cubed, the conversion factor must also be raised to the same power. Let's begin. We are given a density of 7.85 grams per cubic centimeter. First, let's convert grams into kilograms. Since 1 kilogram equals 1,000 grams, we multiply by the conversion factor 1 kilogram over 1,000 grams. Notice that the gram unit cancels out, leaving kilograms. Next, we need to convert cubic centimeters into cubic meters. Here's where many students make a mistake. Some students simply use the conversion 100 centimeters equals 1 meter, but they forget that the unit is cubic centimeters, not just centimeters. Since the length unit is raised to the third power, the conversion factor must also be raised to the third power. In other words, 100 centimeters over 1 meter, all raised to the third power. This allows the cubic centimeter units to cancel correctly, leaving cubic meters. After simplifying the expression, the final answer becomes 7.85 times 10 to the power of 3 kilograms per cubic meter, or simply 7,850 kilograms per cubic meter. This is the commonly accepted density of structural steel, and you will encounter this value frequently in engineering mechanics, structural analysis, and reinforced concrete design. Before moving on, remember this simple rule. Linear units use a first power, area units use a second power, and volume units use a third power. Keeping this in mind will help you avoid many calculation errors. Now that we've applied unit conversions involving exponents, let's take our calculations one step further by working with SI prefixes such as milli, mega, and giga. Instead of simply converting one unit into another, we'll perform mathematical operations while applying the correct engineering prefixes. In this example, we'll evaluate several expressions and express the answers using the most appropriate SI prefix. Whenever you encounter SI prefixes in engineering calculations, always remember this procedure. First, convert each quantity into its base SI unit. Second, perform the required mathematical operation. Third, express the final answer using the most appropriate engineering prefix. Let's solve each part one at a time. Our first expression is 50 millinewtons multiplied by 6 giganewtons. Let's begin by converting the prefixes. Recall that milli means 10 to the power of -3. Giga means 10 to the power of +9. Replacing the prefixes with their corresponding powers of 10, we perform the multiplication. After simplifying, we obtain 300 times 10 to the power of 6 newtons squared. Although this answer is mathematically correct, engineers usually express results using a more practical SI prefix. Since 1 kilonewton squared is equal to 1 million newtons squared, we can rewrite the answer as 300 kilonewton squared. Notice that the numerical value becomes much cleaner and easier to read. This is exactly why SI prefixes are used in engineering. Let's proceed to the second expression. We are given 400 millimeters multiplied by 0.6 meganewton squared. Again, begin by converting everything into base SI units. Convert 400 millimeters into meters. Convert 0.6 meganewtons squared into newton squared. Now perform the multiplication. After simplifying, the result becomes 144 times 10 to the power of 9 meter newton squared. This may also be written as 144 gigameter newton squared. However, another acceptable engineering expression is 0.144 meter meganewton squared. Notice that both answers represent exactly the same quantity. Depending on the application, engineers usually choose the form that produces a simple numerical value while keeping the units easy to interpret. Now, let's solve the final expression. We are asked to evaluate 45 meganewtons cubed divided by 900 gigagrams. As before, begin by replacing the SI prefixes with their corresponding powers of 10. Convert mega into 10 to the power of 6. Convert giga into 10 to the power of 9. Simplify the numerical values and powers of 10. After completing the calculations, we obtain 50 kilonewtons cubed per kilogram. Notice that we again express the final answer using an appropriate engineering prefix instead of leaving the result entirely in base SI units. This makes engineering calculations easier to read, communicate, and interpret. Before we end this lesson, let's review the important engineering rules that we applied throughout these examples. Always arrange conversion factors so that unwanted units cancel. Use dimensional analysis instead of memorizing formulas. If a unit is squared or cubed, the conversion factor must also be squared or cubed. Convert SI prefixes into base units before performing calculations. Keep several decimal places during intermediate computations and round only the final answer. Finally, always check whether your final units and numerical answer are reasonable. Developing these habits early will help you solve engineering problems more accurately, not only in engineering mechanics, but also in mechanics of materials, fluid mechanics, thermodynamics, steel design, reinforced concrete design, and many other engineering courses. That wraps up today's lesson on applying numerical calculations through engineering examples. I encourage you to work through these examples on your own before watching the solutions again. Remember, the best way to improve your engineering skills is through consistent practice. Before you leave, Here are a few more numerical calculation examples for you to practice on your own. Feel free to pause the video, solve each problem at your own pace, and then compare your answers with your own calculations. Let's start. Example number 1. Example number 2. Example number 3. Example number 4. Example number 5. Example number 6. Example number 7. Example number 8. Example number 9. Example number 10. Example number 11. Example number 12. Example number 13. Example number 14. Example number 15. If you found this video helpful, please like this video, subscribe to my YouTube channel, and turn on the notification bell so you won't miss our upcoming engineering mechanics lectures. Thank you for watching, and I'll see you in the next lesson. Bye.